Hello, this is Dr. Strickland. In this video, we will investigate the Wittig reaction. Take a minute to read through these student learning objectives. These are the things you should be able to do by the end of this video so that you're ready for the things we will do together in class. Now, the Wittig reaction, like an elimination reaction, is used to create a carbon-carbon double bond in a molecule. The advantage of using the Wittig reaction is that this reaction is completely regioselective. Only one alkene is formed. In addition, there's no competing substitution reaction. So let's take these one at a time. Okay, completely regioselective means you don't have a major and a minor product as you did when we looked at E1 and E2 reactions. And we were talking about Zaitsev's rule. And competing substitution reactions, this is that if you have a substance that's undergoing an E2 reaction, there's usually a competing SN2. And with an E1, there's usually a competing SN1. So this is a big step forward in terms of making carbon-carbon double bonds. So if you look at the general reaction pattern here, I want you to see that this carbon-carbon double bond comes from joining that carbon with this carbon. So basically, the carbon-oxygen double bond, the carbon-phosphorus double bond is being replaced by this carbon-carbon double bond. So let's see how that plays out. We're going to do one of these together, and then I'm going to ask you to do the product for the second one on your own. So when you get a problem, very often it'll look like this, and I would recommend that you just take your ketone and turn it sideways so that you can see the carbon that is going to be involved in the carbon-carbon double bond right there, kind of in a line with the one from this reagent. Now, this reagent here is called a phosphonium ylide. And that's just a classification. Phosphonium and ylide is Y-L-I-D-E. Okay, so if we line it up like that, and we know that the ketone carbonyl is going to get linked with that guy, then that tells me that when I'm finished, the whole phosphorus thing is going to be gone, and my double bond will be here. And actually, the other product is this guy, triphenylphosphine oxide. And the driving force for this reaction is the creation of the phosphorus-oxygen double bond, which is a really strong bond. All right, so let's do a little fancier one. Let's say you had 3-pentanone and a phosphonium ylide that looked like this. All right, so I want you to pause the video and use the general reaction pattern to draw me the product of this Wittig reaction. So pause the video and do that and come on back. All right, welcome back. So again, we know these are the two carbons involved, so it can be very helpful to just put your ketone sideways. Could be an aldehyde, and you don't have to put it sideways if you don't want to. It just helps me. All right, so here's our ylide, and in this case, the carbon has a methyl group and a hydrogen attached to it. So when we're done, the double bond is here, and you can draw it like this if you wish to just keep the pieces looking the same. This is the same as drawing that. And you can name it and put the stereochemistry in it. It's very fancy. So it's very nice to be able to make just one alkene product. In addition, with something like this, it's very difficult to make what's called an exocyclic double bond, a double bond that involves one of the carbons of the ring and then something outside of the ring, because a double bond that would be inside the ring usually is more highly substituted, and so it will be favored as the major product. So this is a good way to make that. All right, so let's take a look at the mechanism. And for this, I'm going to turn them both this way so that the carbon oxygen double bond is pointed up. And then double bond between the carbon and the phosphorus. And I'm going to just line them up like this. And then we need our 3 phenyl groups here. All right, so when it's lined up like this, this is a cyclic set of electron movements. So starts with the attack of the electrophile with the pi electrons of the carbon oxygen double bond, and then these pi electrons will be the nucleophile. And that gives us something that looks like this. So we've got an oxygen phosphorus single bond. Still have bonds here. And now the carbons are joined. Let's see what else we've got attached to these things. C6H5, 3 of those. And then the 2 things that were bonded to that carbon here. And then the 2 that were bonded to the carbonyl carbon here. All right, so this is an intermediate. It's called a phosphooxetane. And now we're going to form the phosphorus oxygen double bond and the carbon-carbon double bond at the same time, which gives us this guy. And this guy. Now, let's just draw a line so that doesn't get all mixed up in it with the phosphorus oxygen double bond. Okay, and that's how it works. Now, I do want you to know how to prepare a phosphonium ylide, and it starts with this guy right here, triphenylphosphine. Now, phosphorus has 1 pair of non-bonding electrons, just like nitrogen does. And this is an SN2 reaction. So the less hindered your alkyl halide is, the better. And we find in practice, this is either going to be methyl halides or primary alkyl halides. But this is just the replacement of the bond between phosphorus and carbon with the one between carbon and the leaving group. And so we get an intermediate that looks like this. Created a single bond here where the nucleophilic attack was done and the leaving group was kicked out. And now to go from here to the phosphonium ylide, what we're going to do is we're going to use N-butyl lithium. So CH3, CH2, 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 Li. Okay, it's just an alkyl lithium, and sometimes it's abbreviated like this. N-butyl lithium, extremely strong base. And I'm going to pull down one of these hydrogens because the base, you know, this is an organolithium compound. So the covalent bond that joins the carbon and the metal acts like an anion, and it's going to remove this hydrogen, and we're going to put those electrons right up there. Now, oh, I forgot, this phosphorus already has a positive charge because it has 4 bonds. So let's see what happened. Got a positive charge there, and then this guy is now an anion. And you can also draw this by something that's like a resonance structure. Just a different way of drawing the polar covalent bond that exists between the phosphorus and that carbon. All right, so that's how it goes. So I want you to answer the question at the end of this video, and then I'll see you in class.